and all the inequality constraints should be greater than equal to type. This one is given as a less than, so also convert it into a greater than equal to sign. Okay, and the variable bound here x1 greater than equal to 0 should also be treated as an inequality constraint. Okay. All right. So, what is your fx then? The function value? Function plus 2x2, and h1x minus 4. Yes. So minus 4 should be in the left hand side when you write it as h1. Similarly, g1 x2 square, right? And g2, the second inequality constraint, just x1 is x1. So now you have all the functions. You can use the formula for the KKT conditions, the equilibrium conditions, feasibility. All these you can write down. Should find it. Page 12. So your problem has to be in the format given on the top of page 12, the top right box. And then the bottom right box talks about the KKT condition. So these are the things now you have to write. So the gradient of f you can write, right? Del f over del x1 and del f del x2. Write that as a vector form. Any question, doubt? Then you use the KKT conditions from page 12. So write the gradients, gradient vectors of f, gradient vectors of g, and gradient vectors of h. Okay, then there will be u1, u2, and v1. So you first write this down. Write the KKT conditions as it's given there for this problem. Yeah, write the general form now in terms of x1, x2. Okay. If you have written that, now go to part A, where take the first point 0, 4, x1 is 0 and x2 is 4, and then substitute on your conditions, KKT conditions, and then try to find out a U1, U2 and V1 that will satisfy all these conditions. So right now you're writing a general expression for KKT condition for any x1, x2. Then I've given you here 2 points to be checked, 0, 4 and 3.4, minus 2.8. So check them one by one to see if you can find for each of these, can you find a respective U1, U2 and V1 that will satisfy all the conditions. Okay, so the first equation will be a vector equation, right? Okay. So you can write them into two different equations. Okay.
First point we are able to calculate the U and V vectors.
So that means what?
KKT.
That means it's a KKT point. Yes. Right.
So the coefficient turns out to be for x1 it is minus 4.
Which coefficient you're talking about?
So the coefficient we have for each inequality and equality constraint.
Oh, the U1, the Lagrange multipliers, U1, U2.
U1, U2.
What is the U1 value you're getting?
So one is 0 and another one is minus 4.
So it cannot be minus. U's cannot be minus. V can be minus. So the V1 for the equality constraint, it can be positive or negative, but U's cannot be positive or negative. So if you get negative, that means it's not a KKT point. It doesn't satisfy the last condition, so it's not KKT point. U2 value is negative? Huh?
We cannot obtain U2 and V value.
You cannot? Yeah, see, all the conditions you have to use. You should be able to calculate all conditions, not just one. But there are so many conditions. Everything has to be used. Usually the equilibrium condition and the complementary slackness conditions help you get that. But you also have to check if the feasibility conditions are satisfied.
Yes, sir. Put x1 equal to 0, x2 equal to 4. Reduce to this. x1 0, then minus u2 minus 2 minus 0. Minus 0.
So is greater than 0. Okay. So 0, 4, what's happening? Is it a KKT point? No. Okay, let's try the other one. So what is the U1, U2 you are getting at the first point? 0, 4. So U1 is 0, right? And U2 is minus 4. So obviously this doesn't satisfy the condition. Okay. Now let's find out for if one is not satisfied, we don't have to compute V1 really. Everybody solved the first point for the first point? No, sir? Where are you stuck? Have you written the equations?
We got two equations and three unknowns, sir.
Okay, check all the conditions. You should be able to figure it out. Okay, how is the complementary slackness condition? So at 0, 4, so you have one of them that says U1 times 19.4 minus x1 square minus x2 square equal to 0, right? Right. This is one of the complementary slackness condition. So at 0 and 4, what's happening? This term is positive. So U1, this says U1 has to be 0. Okay. The other condition is U2 times x1 should be 0. That is with the G2. U2 times x1 equal to 0. So x1 is 0. So in x1 is 0, U2 times 0 equal to 0. That doesn't tell me what the U2 should be. U2 can be anything. So from this I cannot get any information. So this is kind of useless. But at least I got the information that U1 equal to 0. Can you now find U2? Some people are finding minus 4, but I'm asking those who couldn't do yet. Because now you got this information that U1 is equal to 0. So any constraint that is inactive at the point, the corresponding U has to be 0. Right? How about you there? You are working? You are finding? Yeah? Okay. So what I am showing you here, I just tried to make the sketch of the feasible region. So here is the circle, okay, that's x1 square plus x2 square equal to 19.4. It is slightly more than 4, because if the right hand side were 16, it would have passed through 4. So it's 19.4, between 4 and 5. Okay, and the region inside is feasible. How do you know? Take a point. So this circle divides the whole region into two parts. One is inside the circle, one is outside the circle. So take any point inside the circle. I can take 0, 0 and put into the equation of the constraint equation. You see whether it's satisfied or not. If any point inside satisfies the constraint, every point inside will satisfy the constraint. So if I put 0, 0, you see that this is satisfied, because 0 plus 0 is less than 19.4, right? So everything inside the circle is feasible, outside the circle is infeasible. Now I go to the next constraint, which is x1 greater than equal to 0. x1 is the y-axis line, right? Greater than equal to 0 means the positive side is feasible. So that's why I put this thing saying this side is feasible. So now you see this half circle, half of the circle is feasible. But now I have one more constraint, which is equality constraint. That's a linear one. 2x1 plus x2 is equal to 4. Here is that line. Now since every point on the circle has to be feasible, and the two inequality constraint makes this half feasible, so where is the feasible region? Only the line going from this point to that point. That's this green line that I've drawn. That's the feasible region. So optima has to be one of the points between these two ends. So I've given you actually the two ends. This point is the first point, 0, 4, and this point is the other end, which is 3.4 and minus 2.8. Okay? Now, in order to find graphically which is the maximum point, you need to be able to draw the contour of the objective function. So what is the objective function? It's a parabola, right? It says 3x1 square minus 2x2. So in order to draw a contour, you have to assume some value. Let's say I assume a value of 3. And I want to draw the contour where every point on that line will have a value 3. So can you now plot this graph? 3x1 square minus 2x2 equal to 3. So this is a parabolic equation. So 2x2 is 3x1 square minus 3. You know how to draw the parabola? it will be like a parabola. So you see that parabola will be this one and going this way. So any point on this parabola line will have a value 3. So this is the only feasible point. So here if you have a point, that's going to have a function value 3. Let's draw one more to see which way it's increasing. Let's now assume that this value is 0. So 0, it will pass through the origin, and this is the parabolic equation. Okay, so this anything on this line will have a value 0. So you see that if you are going up with the parabola, you will have a reducing in function value. But I want to maximize, so I have to go in the opposite direction. So that means if I go down, it may be 6 here, it may be 9 here, and so on and so forth. So now the 6 one is going to hit here, 9 may be hitting here. So which is the maximum point now? Point 2, because that's the last point it is going to go through this big parabola that here. Anything here, you will have a much bigger function value, but there is no supporting feasible point. So that says this is the optimum, this is the maximum. If I asked you to minimize, which point you would have gotten? 0.1. Okay, so this is graphically, you can only solve up to 2 variables, not more than that. So this problem, sometimes it's better to draw graphically and understand what's going on, and then use the theory and the algorithm to see if you're getting there. So 0.2 should be a KKT point. So 0.1 is not a KKT point, right? And it should not be, because that's not an optimum. So a non-optimum can be KKT point, but need not be also. So I'm not surprised that this is not a KKT point. But if you tell me 0.2 is not KKT, I'll get surprised. So you should get that as a KKT point. Let's check.
But how do we find out these U1s and U2s?
Yeah, all the conditions that are given, you should be able to find out. The complementary conditions are the first thing you have to check. Complementary conditions, for example, I showed you on the first problem, the complementary conditions tells me U1 is to be 0. Because U1 times this should be 0. At this point, x1 is 4, x2 is 0, x1 is 0, x2 is 4. So 19.4 minus 16, which is 3.4. So 3.4 times U1 is 0, so U1 has to be 0. So that's how you get U1. U2 I cannot get from the second equation, because x1 is 0. So U2 times 0 equal to 0 can happen for either U2 equal to 0 or any value of U2. So I cannot determine U2 from this. But then I have the equilibrium conditions, where I can now plug in U1 equal to 0 and I can get U2. So all conditions you have to use to get the values of U1, U2.
For the second case, sir, this inequality x1 turns out to be inactive.
Yeah, x1 is inactive at that point. So U2 should be 0 for that.
Sir, U2 is coming to be
0, but U1 will be non-zero.
Yes, sir, 1.35 it is.
Should be positive,
Yes.
1.35. And what is V1?
Minus 5.56.
1.35, U2 0, V1 is minus.
5.56.
Yeah, there is no restriction on V1. It can be anything. So this is a valid solution, right?
Yes.
Condition. So that means it's a KKT point. All it says, if you can find one set of U and V that satisfies all the conditions, then it's a KKT point. In order to say further, then you need those necessity condition that we talked about. Now you have to check what about the gradients at this point, are they linearly independent or not? So those are needed. But here we don't need all that. Everybody got the first part? 0, 4. You should ask me if you are not getting it, means there is something you don't understand still, and I'm here to tell you that. And the purpose again should not be just solve this problem. I mean, you should try to understand what's going on. So if there is a quiz question, you should be able to solve yourself, right?
Shall we implement KT sufficiency theorem?
Yeah, now those of you who have done that, you can try that. See if it satisfies the sufficiency condition. Did you find a u1, u2, v1 that satisfies all conditions for 0, 4? What is your u1, u2? So does it satisfy all the conditions? Check all the KKT conditions. Does it satisfy every condition? Yeah, there are several KKT conditions I have, right? Does it satisfy all the conditions? Check it. There is a last condition that says all u's should be greater than equal to 0. So you just told me that is minus something you got. So that means it doesn't satisfy. So it's not a KKT point. Right? Second point. Yes. Now, yeah, substitutes x1 equal to 3.4 and x2 equal to minus 2.8 and check again. So over this side at the back, does everybody got the first part 0, 4 and it's not a KKT point, right? Did you find it to be not a KKT point? Everybody? Please raise your hand if you haven't found it. So where are you stuck? Are you able to solve for u1, u2? No? Minus 4.
0, minus 4 and v1 is also.
Okay, so minus 4 is not allowed, right? Because the last condition doesn't get satisfied. Last condition says u1, u2 should be greater than equal to 0. So that means this point is not a KKT point because it doesn't satisfy all conditions. Is that okay? How about others? Have you all got the same way? Okay. Now move to the next point. And as I just shown you through this graph, it has to be a KKT point. See if you are getting that. If you're checking the sufficiency theorem, you have to first convert it into minimization problem and the way the problem description is, right? So is this a convex objective function?
So for x1 it is not.
No, the objective function 2x2 minus 3x1 square is not a convex function.
It is not, sir.
It's not a convex objective function. So you cannot use the sufficiency theorem. Yeah, that's it. You're stuck there. You can't use. And I didn't give you any further generic form of sufficiency theorem, so you will not be able to check sufficiency theorem for it. But what you could do is you could do some sensitivity analysis now. So you can say, what if I change this circle from 19.4 to say 25, increase it to 25? Then how much will be the change in my function value? You can compute that. Or I can change the equality constraint from minus 4 to minus 5.
Is that talking about it in B part, sir?
Yeah, solve the B part then. Solve the B part. Mm-hmm.
So for the B part,
For the B part, what is the delta B? What is the change in B? And what is the corresponding Lagrange multiplier? So only equality constant is changed, right? So look at the formula that I have given you for the sensitivity analysis, which is in page 4. 4? Why is it 4? The page number is not given, but 38, page 38. Okay, so the delta F expression is there on the top left figure, at the bottom, delta F star. Use the last equation. So here only V, delta alpha 1 and delta alpha 2 is 0. For the first, the inequality constraints are not changed. So there is no change there. Only change is in the equality constraints. So that means delta beta. What is delta beta? It was 4, now it is changed to 6. So plus 2. And what is V1 you found for that? So now you take a product, and that's the change in F you expect. So how much change you are getting?
so it's negative
Negative?
minus 11.12.
Okay, so negative for this minimization problem,
Yes, yes, sir.
right? So in the maximization problem, it will be positive,
Positive.
right? And 11 point something, right?
Minus of,
Yeah, so here is what I've tried to plot again in blue. So blue is the new line, okay, because it moved up. The equality constant have moved up. And now your feasible region is from here to there. So this will be your new optima, because anything here. So this is going to be having, I'm sorry, wait a second, what did I do here? I was minimizing, right? But I considered maximization there. So now you have a smaller value, yeah. So you have a smaller value than what you had. So this one, will you have a larger value? Wait a second, did I actually used the maximization here, right? That's how we get that, okay. So what was the value here? Did you compute the F at this point? There will be some F. Let us compute that. What was the F at this second point? 40.2. So x1 is 4 point, I forgot what was that, x1. X1 is 3.4, sorry, 3.4 and minus 2.8. So 40.8, is it? Okay. So is it minus or plus?
it will be minus, sir. In the minimization problem.
Minimization will be minus. So it will be minus 40.8. Okay. So now as I see it, it's going to be little bigger than this when we go up, because this is the minima, so this is not going to be that. So but it's difficult for me to say whether it is going to be smaller, because these two both are curved. So yeah, both are curved. I don't know which one is curving more, the circle or the parabola. The gradient will tell me that.
What we can guarantee, sir, it will decrease.
But the sensitivity analysis is saying
It will decrease.
it will decrease. Decrease on the minimization function.
Yes, sir, minimization function.
Oh, so it will get better. Okay, maybe. Then the parabola is curving further. The best thing would be if you get the intersection of the blue line with the circle and actually get the point and compute the function value there. That will be the best way we know. Because this one we know 40 minus 40.8, we would know how much is that. So why don't you solve the new line with that? Okay, but the second point, did you all find? That's a KKT point, right? Okay, so then let's move to the second part, B, where you need to now do the sensitivity analysis. So the B says that how would the maximum function value change if the equality constraint is changed to 2x1 plus x2 equal to 6? So how much is the change in the right hand side? It was 4 before, right? So it's a plus 2. Okay? And so how much is the change with the sensitivity analysis that we talked about in page here 38. 37, page number is not given, but it's 38 page. Okay, see the formula on the top left slide. Del F star is the product of the Lagrange multiplier and the change. So there are two inequality and one equality. Which one's right hand side has been changed? Equality, right? The inequalities, there is no change. So the first term is only with inequality. So delta alphas are all 0, but delta beta is changed to amount of 2. So delta beta is 2. So you have to multiply that with the corresponding V. So what did you find that? Minus 10.6? You found something else, I guess. Into 2.
Even if minus 5.56. Oh, so that will be minus 11 point something. Minus 11, right? Yes.
Minus 11 point. Okay. So that's your V1 multiplied to 2. Because 2 is the change. 2 is delta beta and V1 is what you found. When you take the product, that will be the change in F. Okay? So that will be the change in what F? On the minimization function that you have written. So what will happen to the maximization? It will increase. Yeah. So the point gets better actually. That point gets better than the earlier situation.
Intersection point which we were discussing about,
Yeah.
turns out to be x1 is equals to 3.96
Mm-hmm.
and x2 minus 1.92.
And have you computed the function value there?
Just calculating it.
Do the minimization one. 2x2 minus 3x1 square.
Minus 50.88 it turns.
Okay, so it gets better.
Yes. And difference is also almost
Difference is almost 11.
3 volt.
Yeah.
Sensitivity analysis performing quite well.
Yeah, quite good. So, yeah, it works pretty well actually. You see, and because this circle is curving and the parabola is also curving, it's very difficult to say whether it will increase or decrease. But sensitivity analysis can tell you the right thing, that whether it will increase or decrease without doing anything further. So it's really very powerful.
So how to for the second case, B part, sensitivity analysis.
Yeah.
How to do start with?
So you look at page 37. There we talked about the sensitivity analysis. The very last equation on the right, del f star, 38, I think. 38, yeah. Sensitivity analysis. So you have this equation del f star equal to sum of ui, uj delta alpha j plus vk beta delta beta k, right? So this delta alpha and delta beta are the change in the right hand side of the equations. So what I asked you to do is only change the equality constraint. So that means the inequality constraint, there is no change. So delta alphas are 0. So only is delta beta that has changed. So how much is the change? It was 4 before, now it has become 6. So there is a change of plus 2. Yeah, so delta beta is plus 2. And that requires the corresponding Lagrange multipliers V1, which you found, right? Which you found for that point. In part A. Part A you have found V1, right? So what is the V1 you found for that last point, second point? So that is your V1 multiplied by delta beta will give you the net change in the function value. Yeah, so that is how to do it. Okay, everybody got that? Who hasn't got that yet? I can clarify once again if you have not, because this is really the very important thing that we're talking about, and it's very simple concept. You just have to think a little bit and use the formulas I've given you, but take this example as a way to understand the power of sensitivity analysis and the Kuhn-Tucker conditions. Here we are assuming the second point is an optima before you do part B. Part B is valid only for optimal points, right? And graphically I've shown you that is the optimum. That's why we could do the sensitivity analysis. So sensitivity analysis, after you found the optimum, right? You are trying to see what if I change my constraint, mainly the right hand side, the parameters, which is usually the resource. If I change it, how my objective function is going to change. That's exactly what you could do. So for that you need the Lagrange multipliers, okay, at the optimal point and the change in the right hand side of the constraints. Yes. So that's the V1 corresponding to that optimal solution, right? Yeah. U2 is not important. U2 is important to say out of the two inequality constraints, which is more important. So if you get U1 equal to positive something, 1 point something, and U2 0, that means U2 is not important for these optima. And as you can see in this figure that I have drawn, U2 corresponds to this line, vertical line, where it's far away from where the optimum is. So U1 is most important. That's the only information you get from that. Now when I change the constraint to the equality constraints, then V1 becomes important, because V1 times the change in the constraints will give you how much change you are expecting in the objective function. And he has computed the new point. He has found the new point, and it seems the change is more or less the same as you are predicting through sensitivity analysis. Yeah. Yeah, general equation is always valid with any kind of changes. Yeah. V1 turned out to be negative, right? Yeah, can be negative, yeah.
So what is the significance of that?
Okay, why can be negative? Why not the inequality? Well, equality constraint, what is the equality constraint? 2x1 plus x2 equal to 4. So I can write it this way. Okay, I can also write it minus 2x1, I can multiply it by minus 1 plus 4 is equal to 0. So I can do hx equal to 0 or minus hx equal to 0, same thing. So if hx has v, minus hx should have minus v. So it depends on which one you have chosen. It can turn out to be a negative value, but if you had used the other one, you would have gotten a positive value. But for inequality constraint, that's not true. inequality constraint, when you say this, you cannot now say minus of this is also greater than equal to 0. Then sign changes, but that's sign changes means you have to get it back into this sign again. So for inequality constraint, this is the unique way to represent the constraint. But for equality constraint, this is not the unique way. I could also do this way, and then I will get a reversal in my sign. So that's why sign is not important. It just depends on how you have put your hx.
So in those books where the inequalities are
Less than.
They are the
Still u's are going to be positive. It's just that your equilibrium condition sign changes from minus to plus. But u's are still positive. Why u's are positive has a deep meaning. I need at least half an hour to explain, but several sketches are needed for me to explain. Maybe sometime if I have time I will do. But it's very interesting how the u's come out to be non-negative. Okay, I think we need to stop now and go ahead with the quiz. Okay, because then others will run out of time. So again, we agreed that you can complete it if you have not completed at home and bring it tomorrow morning. This is just one problem. Okay. Exams, I don't think you need to look at anything. So please keep aside everything. Keep away even the slides and everything away, so we can start the quiz. They have to work on their own paper, right? Yeah, so please take out some papers where you'll be working on. And try not to look around, just do it yourself.
Please collect your first assignment paper.
So the first problem, you write 1 and then A, and then first say whether it's true or false, and then write at least one line explaining why you think so. And then move to B and C, all that. If needed, you can draw a sketch to explain. It's up to you.